Hi ladies, this is Mrs. Blaufuss here. Today we are looking at circles. So this is 1.7 in your Discovering Geometry textbook. We have a bunch of new terms. So make your flashcards or put them in your Quizlet because there are a lot of terms that go along with this unit. So we're going to start just by looking at a diagram and using those terms that are on the top of your note sheet. Let's label these diagrams. The first one, point P, this is the center. When we talk about circles, we define circles by their centers. So I would refer to this circle as circle P because it has a center point P. The second one is talking about a segment, and it's talking about this segment from the center of the circle to any point on the outside of the circle, and that's called a radius. And then the second diagram, we're looking at a segment again. It goes through the center of the circle and touches the outside of the circle with both endpoints, and this is called the diameter. If you notice, the diameter is made up of two radii. Here's one radius. I'll highlight that in green. Here's one radius. And then a second radius coming from the center to the outside of the circle is in red. A diameter is one consistent segment that goes through the center, and it's equal to 2 times the radius. Okay, so let's look at some definitions, and these are right from your textbook. You could get them from your textbook too, but on your note sheets, please just follow along. So a circle is the set of all points in a plane at a given distance from a given point. Okay, that's kind of wordy, so let's break it down. So here's a given point. We'll just say that this green point right here as the center of the circle being the wheel of the bicycle. So it's the set of all of these points. All of these points are the same distance away from that center of the circle. Okay, the next term is radius, and that's the point that we just labeled. It's a segment from the center to a point on the edge of the circle. It is the given distance. Okay, so all radii are the same. So that is the distance from the center to the circle. This says all radii are equal in a given circle. And then the third term, center, that is the given point between the radius and the center of the circle. Between the radius and the circle. So if you were in class, you got this note sheet and it had examples of chords and some examples of not chords. I want you to pause the video for a minute, and there are 3 terms: chord, diameter, and tangent. So pause the video and see if you can come up with your own definition of a chord and a diameter. You can pause the video while you work, and you can unpause for the solution. Okay, the definition of a chord, if you notice in all of these examples, a chord is a segment, and in all of these examples, the endpoints of the segments are on the circle. A diameter has a similar definition. It's a segment, it has endpoints on the circle, but a diameter must go through the center. If it doesn't go through the center, but it follows all of the other criteria, then it's just a chord. Okay, now take a minute, look at these tangents and not tangents, and see if you can come up with the definition. You can pause the video while you work and unpause for the solution. The definition that we have for a tangent is a line that intersects the circle at exactly 1 point. So notice all of the tangents, those lines do not go through the circle. They intersect at just a single point, here at point C, here at point B, and here at point F. You'll see this written as the point of tangency. Okay, so we call that point the point of tangency. So C is a point of tangency, F is a point of tangency, and B is a point of tangency. So just on your own, think of this question. Can a chord of a circle also be a diameter? Can it be a tangent? Explain why or why not. So take a minute, pause the video while you work, and you can unpause for the solution. The answer to this first question, can it be a diameter, is yes. Because a chord is a segment where the endpoints lie on the circle. That's true for a diameter too, but remember diameter is a specific chord. However, that's not true for a tangent because in a chord, the segment meets the circle at 2 points. It has to because both endpoints have to be on the circle. But a tangent meets only at 1 point. It does not cross through the circle. A tangent has only 1 point that lies on the circle. Okay, and then the second question, can two circles have a tangent of the same line at the same point? Draw a sketch to explain your answer. So again, pause the video while you work, and then you can unpause for the solution. And the answer to this question is yes. And here is just one example. This point right here, it doesn't cross through the two circles. It just is the point where the two circles touch. And then this tangent too, it does not cross through the two circles. It is only passing through that specific point. There are multiple ways you could draw this. I will draw another example. So here's one circle. I can draw the other circle. Well, I'm actually going to draw it next to it. Okay, I'm going to draw it right here. You can see that these two circles just barely are touching. And they touch at this point right here. So I can draw a line through that point so that the line does not cross through the circle, but it just simply touches it. Okay, so I could do that in a variety of different diagrams that look pretty much the same, but maybe just have a little variance, maybe the size of the circles or the location of the shared point. But yes, two circles can share a tangent. Okay, so we have a couple terms, congruent. This is a familiar term, or it should be a familiar term. We've talked about congruent segments, congruent angles, congruent polygons, and now we're going to talk about two circles that are congruent. Circles are only going to be congruent if they have the same radius. Okay, remember, a circle is a set of points from a given point, and that distance between those, the point and the circle, is the radius. Okay, so any circles that have the same radius are going to be congruent. And then secondly, concentric circles. Those are circles that are on the same plane that share the same center. Okay, so CDs, these are examples of congruent circles. But something like a target, maybe you shoot archery and you're shooting at a target, or riflery and you're shooting at a target. All of these circles, all of them have the same center. Okay, so this point right here is the center of those circles. They're not the same. Those circles don't have the same radius, but they do share a center. Same is true with a ripple. Okay, in real world examples, all of these circles share that center point. They're not the same size. Those circles are not congruent, but they do share the same center. So here are a couple examples of things that are circumscribed. Okay, the circle circumscribes the triangle or circumscribes the quadrilateral. So in class, we worked on developing definitions. So the definition that we have for circumscribed is a circle is circumscribed about a polygon. That's how we'll say this. If and only if it passes through each vertex of the polygon. Okay, so you can see here, each vertex lies on the circle for both of these examples. If the circle is circumscribing the quadrilateral or the polygon, that means that polygon is inscribed within the circle. Okay, here we're just really focusing on this top part of the definition because we're focusing on circles. So let's see if a circumscribed circle touches the vertices, what does an inscribed circle do? An inscribed circle touches each side of the polygon. So the circle is inside and it touches each side. Okay, so a circle is inscribed if and only if it touches each side of the polygon at exactly one point. Notice it's not going through. Okay, our circle is not going through the polygon. Something like this. Yes, it touches each side, but we have to specify that it touches each side exactly once. So how do we write all of these things? Well, when we're talking about a set of points within a circle, we call that an arc. Okay, so it's not a segment, but it is an arc. So an arc consists of points on a circle and the continuous part of that circle between those 2 points. Arcs do have endpoints, so we're going to name them similarly to how we name a segment, but with arcs, we have 2 types of arcs that we'll talk about in just a second, but we're going to use 2 or 3 letters. And instead of using the segment symbol, we use this arc above the 2 endpoints that looks kind of like the arc of a circle. Okay, our definition is semicircle. A semicircle is half of a circle, so the endpoints of a semicircle are the endpoints of a diameter. Whoops, here we go. We have to label an arc of a semicircle with 3 letters. If we only label it with 2 letters, we may think that we're talking about the diameter. So we're going to use the 2 endpoints, which are the same as the diameter, and some point in between. Then we have a minor arc and a major arc. A minor arc is an arc that is smaller than a semicircle. Okay, and with a minor arc, we can use only 2 points. But with a major arc, that's an arc that is larger than a semicircle, and we need to use 3 points for that. Okay, so 2 endpoints of the major arc, and then some point in between. Okay, so your definition sheet looks something like this. An example of notation for an arc, and it can be any arc. So this is an example of a minor arc. Okay, so notation might be arc PD, or I might say this arc, and I would call that arc PAD. Okay, so I'm still using the endpoints. We can measure arcs. And just in the definition here, I'm asking for the arc of a full circle, and we measure arcs in degrees. Okay, so a full circle or a full rotation around a specific point measures 360 degrees. A semicircle, I'll name a semicircle here. This is arc APD, and a semicircle measures half of a circle. That's 180 degrees. A minor arc, again, we can name a minor arc with just 2 points. So it might be arc AP. And the measure of the arc is going to be the measure of what we call the central angle. Okay, and in a minor arc, it's going to be less than 180 degrees. And it would be this angle right here. And then a major arc, so a major arc might be right here, D to A to P. And there are several examples, I'm just giving one. And the measure of this would be the measure of the reflex angle. Okay, so that's going to be greater than 180 degrees. So it would be from this point all the way to that side. So a full circle has an arc measure of 360 degrees. A semicircle has a measure of an arc that's half of a circle. So that's 180 degrees. And then you can see this diagram. This is right from your textbook. The vertex, when we're talking about a central angle, the vertex is going to be the center of the circle. And the shortest distance between those points, or the shortest degree rotation between those two sides, would be a minor arc. And the larger rotation between the two sides would be the reflex angle. So if you remember that from the first unit. So arc measures of a minor arc are equal to the central angle, and arc measures of the major arc are equal to the reflex of the central angle. The central angle, again, being the shortest distance between the two sides that make up the arc, the two radii that make up the arc. Okay, and then we have a last example. So it says, use your compass to draw two circles with the same radius that intersect. Okay, so to do that, I'm just going to put a point for my center, and I'm going to use my compass. And to make sure the radii are the same, I'm just going to leave it open the same amount. Okay, so I'm not going to adjust the opening of my compass. I'm going to leave it just like this. Okay, here is one circle. And here's the center of my other circle. Again, I'm not changing the width of my compass. I'm going to keep it just as it is. And I can draw that other circle. Okay, now I'm done with my compass. So I'm going to get rid of this. And it says label the centers P and Q. Doesn't matter which one is which. Here's P and here's Q. And then it says label the points of intersection A and B. And then it says construct using a straight edge only. Construct a quadrilateral PAQB. So quadrilateral that goes from P to A to Q to B and then back to P. And the question is, what kind of quadrilateral is this? What's the name we're going to give this? Well, first we have to think of what its properties are before we can name it. And if you look at segment PA, that's a radius. And if you look at segment PB, that's also a radius. We know that all radius within a given circle are congruent. BQ is a radius of the purple circle, but we know that these two circles have the same radius. Therefore, BQ is the same as PB and PA. And then lastly, QA is also a radius, so we know that it's the same distance as the other three segments. So what kind of quadrilateral do you know that has four congruent sides? Now we don't know anything about the angles, we just know that the sides are congruent. Therefore, this is a rhombus. Now you might also have a square, but we don't know that for sure because we're not measuring the angles. Mine doesn't look like a square, but I do know that all four sides are congruent, therefore I know it's a rhombus. So that's all of circles. We spent 2 class days in this, and then we did some extra practice on the homework assignment. So please, as you're trying the homework, jot down any questions that you have or questions that you've had while watching this video and bring them to class next time I see you. Thanks.